Hi, welcome to this video on particle accelerators, part of the particles topic for higher physics, and the section on the forces on charged particles. What we're going to look at are the different types of particle accelerator, how they work, and in particular looking at the function of the electric and magnetic fields, of which we've learnt about already. So what is a particle accelerator? It's really any object that is speeding up a beam of particles, and it's the electric fields that are used to accelerate the charged particles. The magnetic fields are used to steer and to focus the beam of charged particles so they can either hit a target or hit another beam traveling in the opposite direction. Particle accelerators will only work with charged particles. If it's a neutral particle, then neither an electric nor a magnetic field will have any effect upon the particle. Particle accelerators often use their own particular unit for energy, the electron volt, or the EV. 1 electron volt is defined as the energy that would be gained by an electron if it's accelerated through a potential difference of 1 volt. So using the work done is charge times voltage formula, W equals QV. 1 EV is the charge on an electron, 1.6 times 10 to the minus 19 coulombs times 1. So 1 EV is 1.6 times 10 to the minus 19 joules of energy. EVs are used because it's an easier way of comparing information. So if you've got 10 EVs, you know that's equivalent to 1 electron being accelerated through 10 volts, rather than just dealing with lots of quite small values in joules. So particle accelerators were invented to provide energetic particles to investigate the structure of atomic nuclei. Prior to the invention of particle accelerators, people would put equipment up into space to look at cosmic rays, charged particles from space, and the collisions between them. The trouble there was that it was very difficult to predict where they would take place. In fact, you couldn't predict that, and therefore you were putting up your equipment hoping that you would detect the particles, which generally you did, but you wouldn't know when and how. So by having a particle accelerator, that allows you to be able to detect them when you want them. There are 3 different types of particle accelerators. A linear accelerator, something that's in a straight line. A cyclotron, where the particles move in increasing radiuses. These are the things that we saw used earlier when we were talking about the preparation of radioactive materials for PET scanners. And a synchrotron, such as the Large Hadron Collider. All particle accelerators have these in common. They have a source of particles, they have the pipes which the beams travel through. Often these are vacuums. In fact, they're always vacuums so that the charged particles are not going to hit any objects and be deflected. And they have means of accelerating the charged particles, which are electric fields. And some magnetic fields, a system of magnets, usually electromagnets, to steer the charged particles. That's true even for the linear devices because you want to focus the beam of charged particles to hit the target in the exact place that you want. So magnetic fields are used to do this. And then you have a region where there is a target, whether it's a fixed target or whether it's a target of another particle traveling in the opposite direction. Let's look at these in turn, starting with the linear accelerator. The largest one is in California, and the electrons pass through a series of electrodes with electric fields, and these keep the electrons moving rather than using increasingly larger voltages. Now they have to continually change the electric field so that the charged particles are attracted and repelled to increase the speed. So here's a diagram at the bottom. If we've got our electron at the bottom in red, so to go towards D needs to be positive and C needs to be negative. But when it was between B and C, going to the right, then C would have need to be positive and B would have need to be negative. So the tube behind it needs to have the same charge and the tube in front the opposite charge to accelerate it. Notice the lengths are increasing. This is because the speed of the particle is increasing, so the time within that particular length is constant. So rather than to make the time constant, we have increasing lengths, and that allows you to use a constant frequency where you're changing the field. So you're changing it from pos to minus, and you can do that because the time it takes to travel through particle C is going to be the same as the time it takes to go through D, because at point in D it's going faster. And so we can use this constant frequency alternating current to change the electric field direction. And here's a diagram. So the electron gun at the top, there are some rings that they travel around, and you can see that there's a detector in the end, so it's not actually hitting so it's hitting a target, but some can go one way, some can go the other way. The difference can be whether you've got a positive or whether you've got a negative source that's taking place. So here we've got a positron source, which will be the antimatter electron, and by using the antimatter equivalent, then that will have the same charge and the same mass, so the radiuses of the circles for the magnetic fields would be the same. They'd just be the field would be in opposite directions. Okay, so in our linear accelerator, this is just describing what I was talking about here. So it's saying at the beginning, electrode A is negative and B is positive. So the electron's going to move from left to right. Before they pass out of B, it's then made negative and C becomes positive to keep it moving that way. And the length of time in each electrode is the same. So the length increases to keep the time the same. So electrons are traveling close to the speed of light, so the voltages have to be switched over very, very quickly. There's an animation here that I'll share the link with you so you can watch this yourself. The second type of particle accelerator, the cyclotron, uses D-shaped electrodes to accelerate particles in a circular path. The particles start off in the center, and then they are accelerated across the electric field in the gap, and then in the D section, there is a magnetic field that causes them to change direction. So they travel within a circle, and then when they get to the gap again, they are accelerated across the gap. What we need to do there is we need to then make the polarity of the D at the bottom right so that they're accelerated across the gap. So the electric field between the middle parts needs to change to reflect that. Then we have a synchrotron, like the Large Hadron Collider. So this is just like the linear accelerator, but you run out of space if you want a linear accelerator. You need them really, really long to reach really large energies. So they're made into a ring so that the charged particles can keep going round. They can keep being accelerated through electric fields and directed by the magnetic fields. And here we can see a charged particle moving around. This one here is a positive particle because it's going towards the negative particle. And there's 4 silver sections that are where the electric fields are to accelerate through there, and the circles are indicating the magnetic fields, the electromagnets that are causing there to be a force towards the center of the circle, so it moves in a circle. The LHC, the Large Hadron Collider, is the largest particle accelerator, 27 kilometers in circumference and a cost of 2.6 billion to build. It's underneath the border between Switzerland and France, and you can see on the map here they've got 4 particular detectors: the CMS, Atlas, Alice and LHCb. They're looking at different types of things. And then you've got the beam pipes shown on the map here. You can see there's an initial ring to cause some acceleration, and then the particles enter the larger ring. Okay, the UK are involved in this project. Professor Brian Cox is one of the people that works within it, but there are also a number of scientists within Scotland that work on the LHC. Comparison of costs for the Scottish Parliament, the bailout for the banks. About 10 years ago, the cost of the M74 motorway. So although it's expensive, it's not as expensive as any of those. The rationale behind CERN was to be a collaborative effort for good and peace after the Second World War and the involvement of the atomic bomb, the Manhattan Project. And so this was where the first experiment came from. And there's lots and lots of benefits that we've got from it. We've got the World Wide Web from Tim Berners-Lee because of the vast amounts of storage and data. We've got treatments for radiation therapy. We've got an implementation for semiconductors, our PET scanners through our understanding of antimatter, and we've got more awareness of safe nuclear power design. So there's lots of things that have come out, even though the original brief is for scientific discovery. So let's check, did we meet our objectives? There are 3 different types. So the linear accelerator, the cyclotron with the D's, and the synchrotron, the LHC. We need to have the basic parts, so we've got our beam pipes, we've got our electric fields to accelerate the particles, we've got our magnetic fields to steer the particles, and we've got a target where we're going to detect the particles, whether that's a fixed one or it's a colliding target. And as we said there, what do the electric fields do? What do the magnetic fields do within the accelerators? And they apply forces to the charged particles, and from our earlier work we should know a bit about the direction of those as well.